Hello again. This is Andy Dibling, and I'm going to be your instructor today. Today is part 7, lesson 7 of Fluid 2000, hydraulic systems and pneumatic systems. Today we're going to talk about seals. Seals are one of the most underrated parts of the hydraulic system, overlooked often, however, one of the most critical pieces. They are the ones, just like your skin, that prevent contaminants from getting into the system and also help from preventing fluid from getting out. So, few words on leaks. Never, ever, ever go looking for a leak with your bare hand or your gloved hand or any part of your body. Pinhole leaks can often be invisible. However, the system pressure is the system pressure. So if you have fluid that's leaking out through a pinhole that you can't see at 200 bar, it will cut your fingers off. So you want to make sure that you're nowhere near that. And not only that, it'll leave puddles on the floor, slip, trips, and falls, fire hazards. It is toxic, carcinogenic, and if it's injected through your skin at high pressure, can lead to gangrene and amputations. So it's no fun at all. You don't want to have anything to do with it. So never go looking for trouble in terms of leaks. If you're looking for leaks, you want to make sure that you shut the system off first. Never look for leaks on a live system. So some tips for finding leaks. So bleed your system down, or provide another method of safely blanking off or locking out the system where pinhole leaks may be occurring. You can lose a lot of fluid through a pinhole leak, even though you can't see it. Or can hardly see it. Generally, what you see is the dripping from the fluid accumulating on a secondary surface. After it's squirted out at high pressure, hit something and puddled. So what looks like a benign drippy leak can actually be a razor blade. So you have to be careful. So you want to make sure that you're going to focus on places where the leak is most likely to occur. And that's going to be things like fittings and hoses, seals. Suspect fittings that are hard to get at. The ones in the back of the machine, they don't get serviced very often. They may not be tightened or checked. And you want to make sure that everything is cleaned up. You clean, clean, clean. If you suspect you found a leak, clean that area quite thoroughly. Turn it on again, repressurize the system. If the fluid comes back, you know you found your system leak. Okay? But again, you must be very careful when looking for leaks. Never look at it for leaks on a charged system. You find your suspects and go from there. So reliability of the system is in no small part determined by your seals and your fluid. Small leaks only get bigger, and eventually they can lead to burst lines, which can lead to a lot of downtime and extremely hazardous or dangerous conditions. You can have a system pump itself dry in less than a minute if I have a major conductor or hose break. Very important that you make sure that all of your systems are protected from whatever kind of leak that you have. Okay, so your efficiency of performance is determined on that. Now, here's the thing: anytime you have a leak, not only are you leaking fluid out, but you're getting air and dirt inside the system. And dirt can be very abrasive on small surfaces. You will have surfaces in your hydraulic system that are on a fluid film that may be a mil or 2 mil, 1/1000th of an inch, fluid separation between the seal and the rotating shaft. Any dirt in there will act like sandpaper or a file and will gouge the soft metal and lead to leaks that can't be fixed unless you replace the component. So there's different types of seals. There's positive seals and non-positive seals. So positive seals provide zero leakage. And those are things like flat gaskets and O-rings between stationary surfaces, things that don't move. So a ram in a cylinder is something that moves. So there I would have a non-positive seal, but a positive seal might be between your manifold and your directional control valve. Those O-rings in between or the flat gasket on the pump is definitely going to be a positive seal. And they don't move, the components underneath them don't move. Non-positive seals, like I said, are things like motors, spinning parts on motors, rams and cylinders, directional control valves or spool valves, anywhere where you have two pieces of metal rubbing past each other. They don't actually rub past each other. They're usually floating on either butylene rubber or some kind of PTFE plastic with some kind of fluid film in between as a lubrication. So the non-positive seals are designed to leak a little bit, but those leaks are more in the terms of vapor, a teaspoon a day, right? As opposed to, a quart an hour or a liter an hour. So dynamic seals are, of course, between moving parts, and static seals are between parts that aren't intended to move. So a stationary seal is quite easy. The critical things on any kind of a stationary seal is going to be that you make sure you have excellent clean surfaces. You can't have any scratches or burrs because they make their fluid tight seal based on them being no gaps or channels between the surfaces. So if I do have a gouge or a nick by a bolt that leads to the outside, it eventually will find a way to leak. Everything must be very, very clean, right? So you make sure that you clean all the surfaces before you reassemble. Any dirt, foreign matter, oil, grease is removed. If you're using a steel gasket in between, make sure that the gasket is correctly sized and that the dowels are where they're supposed to be. You don't have it upside down, because usually once you crush those gaskets in the first time, you don't get another retry. You need another gasket. Now, generally what you're looking at when you're tightening down a flange is you're going to look like you're going to straighten out a tablecloth. So you'll notice on the rectangle on the right, they call it a spiral pattern, but really what you're doing is you're flattening from the inside out. And on a round surface, you're going to use the star pattern. So you're basically going to be wiggling it in and flattening it down to remove any kind of deformation between the two surfaces. And you don't tighten it up all the way. First thing you do is you put it in and make sure it's going to sit right. And you put in, I like to put in all the bolts finger tight. And I should be able to dog them down finger tight till I start to collapse the washer on there. Once that happens, then I know I'm good. Then I attack it with a wrench. And I'll go 1/3, 2/3, and then full torque on there, depending on the bolt. And you have to be careful of the surface. A lot of times when you're dealing with this kind of a hard bolting seal, you're looking at steel, iron, something heavy duty. If I'm looking at aluminum or plastic, of course, the torque spec is totally different on that, and those housings are designed to flex. So chances are you're going to have some kind of an O-ring gasket as opposed to a flat gasket in there. So gaskets are always made of material that's softer so they can seal. Their softness allows them to conform to any irregularities of the machine, and we're talking about on a microscopic level. Gaskets may be used when pressure changes cause the surface to move apart slightly, and that can be in a pulsating movement in the case of this radial pump. The seal between surfaces is made of lightweight or weak materials, so you want to make sure that the seal is good and that the surrounding parts aren't deflecting. May be used when dissimilar metals join. That is a mouthful. To allow for thermal expansion at different rates. Galvanic corrosion is a big issue in a lot of industrial equipment. Anytime you will have two dissimilar metals together, it's always good to have some kind of a gasket in between there that is reactive with neither one. If I add heat to aluminum and iron, I will get a welding that takes place called galvanic corrosion that welds the two together and actually makes a chemical bond between the iron and the aluminum because there are different electrical charges under heat. Anyway, it's a chemistry thing, but gaskets are often good for that. So the two main gaskets are O-rings and flat gaskets. Flat gaskets are used more on flanges, and O-rings are used on spool valves, things like that. So for instance, here we have a spool valve that's attaching to a manifold on top, and it's using an O-ring. Seals are designed, again, as a static seal. They're not determined to move. There may be some flexing, and the fact that those Vickers manifolds are made out of aluminum means they're a softer metal, and I don't want to be torquing them down hard with a collapsible metal gasket. Pump on the other side, on the other hand, you may have metal gaskets in there that are crushes, that they're crush gaskets, and the reason is because there's a high rate of vibration and rotational motion and torque on a motor, it has to be bolted tight. An O-ring wouldn't be able to stand up to that kind of abuse, more than likely. So when you're installing gaskets, you want to make sure that everything is clean. And if it's, here's the thing, just when you think it's clean enough, clean it again. Seriously. You know, I've changed seals in rotating equipment that will be 300 feet in the air, 60 miles from the nearest highway when it goes into service. You want to make sure that that seal does not leak, because changing it out on the fly costs hundreds of thousands of dollars, right? And again, if there's any dowels on your gaskets, you want to make sure that they're aligned and that the gasket is put on correctly, not upside down. Double check, right? Make sure that the surface is flat and not warped. A lot of times heads will come off of machines like pumps or compressors. And because of the temperature differences and perhaps sometimes a difference in material of the manufacturer, you'll get different amounts of expansion and contraction at room temperature. It's important to understand those things and how they might affect a seal. So be sure to follow the specifications in your manual. You may have to preheat some pieces in order to torque them correctly. All kinds of strange things happen in large industrial machinery. So O-rings here. O-rings are a compression seal. Basically, they're distorted ever so slightly by tightening down the two parts. And generally, you're looking for a 10% diameter gap between the channel for the O-ring and the top of the surface. So your O-ring should be just sticking out a little bit. So when the piece is brought down on it and torqued up, it compresses the O-ring slightly, so it's touching in all four corners, right? They can be used for static or dynamic seals. O-rings are increasing in use because of the materials that we have now for O-rings are much, much tougher than they were 25 years ago. The synthetic rubbers that we have nowadays, not to mention the improvements in fluids and longevity, O-rings now are handling higher and higher pressures for longer and longer service times. So you have different types of O-rings. Viton, which is a fluorocarbon rubber, is great for high pressure seals and is great for UV protection too, chemicals. It's good stuff. So Viton seals are top of the line. You'll see here that you have this backup ring, sometimes called a wear guard, and that's designed to put a little bit of space so that the O-ring doesn't get extruded or ripped to pieces by the normal action of the cylinder. In this case, if you look at the picture of the cylinder on the right-hand side, it's there to, the backup O-ring is there. It's usually made of PTFE, which is a plastic, and it's there designed to protect that O-ring. Generally, O-rings will swell slightly in the presence of oil. Artificial rubber or neoprene is used for low pressure seals and between housings and cartridges where I don't need that high pressure demand, or it doesn't have to be a dynamic seal. PTFE is great for backups. And actually, if you have artificial joints, PTFE is a key component of those as well. So if you're installing O-rings, never, ever, 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 please ever use a screwdriver. You cannot use a screwdriver to remove an O-ring correctly. You will gouge it out. I know it doesn't look like there's a scratch there, but some of those scratches you can't see. Here's the thing. A scratch of 1 thou under 200 bar of pressure will leak. It's not a matter of if, it's a matter of when. Maybe not the first day, but after 2 or 3 weeks or 100 or 200 cycles, and that O-ring wears in and moves around, you will get a leak there. So you want to use the correct tool, and hooks are used to remove and put in O-rings. So it's very important that you clean the channels. And again, if you think they're clean enough, clean them again, because you can't have it too clean. And you want to lubricate your surfaces. You want to pre-lubricate your O-rings when you put them on. So for instance, here we have a simple situation. We're putting an O-ring over a keyway. I don't want to just drag it over that keyway because those sharp edges can cut into that O-ring on the underside and structurally weaken it. So we can put some tape over, or what I like to use is cellophane, just regular everyday cellophane. And that way I can slide it over when it's greased up, the plastic on plastic, into its position, and then remove the cellophane after that. The tape sometimes can leave a residue. Okay. Sealants are sometimes used, especially on piping, National Pipe Thread, or NPT, which is a tapered thread. And remember, on a tapered thread, that you don't want any more than 7 threads per inch. And you want to make sure that you have 5 of those threads that are engaged. The white PTFE extrusion plastic that goes on here, the pipe dope, as it's often called, the sealant, does fill in these little these little channels at the root of the threads, because it's a spiral and it's a continuous leak if it's not filled with this particular material. So it's something to keep in mind. And you want to be careful when you're tightening up pipe threads not to over tighten. That's generally the rookie mistake, is you over tighten, and that will actually induce a leak because you distort the housing that you're screwing into. Lip seals are quite common, especially on rotating equipment. And it's very important that lip seals are put in the correct way so the lip is facing the pressure. A lip seal must remain static inside the bore housing, and after the seal has been exchanged a few times, you may find it doesn't fit as it used to. Usually exposure to rotation, heat, degradation from the atmosphere will harden the seal over time. If I am removing a shaft or I am removing any kind of components on a motor, I just replace the seals. I replace the seals every time. A seal is a few dollars. Really, even an expensive seal is, well, 80 Canadian dollars. So that's what, 20 RMB, right? Sorry, the other way around. Yeah, it'd be about 80 RMB or 20 Canadian dollars. So that's not much to pay for peace of mind. You can never really have, yeah, replace your seals. Clean, tight, and dry is what you want. Now, in a dynamic seal, they are designed, especially if they're sliding, like this one would be on some kind of a cylinder. This cylinder is, you can imagine, this rod would be stroking in and out, the high pressure on the backside here, and that allows this seal to grip against the shaft. This garter spring in here keeps everything honest and compresses the lip seal up against the shaft in case of a slack in pressure. It just keeps it tight up against it to maintain the seal. Now, the seal itself is actually made by a fluid film that is uh, basically microns across. And that is actually providing a film of oil between the shaft and the rubber on the seal. This is a single lip seal. A lot of times I will have a double lip seal if I can get away with it. I generally, if I'm replacing the seal, I'll always ask for the double lip. It's a few dollars more and it's just peace of mind. Can't tell you any more than that. Okay, always put the open side towards pressure on a lip seal. When you're putting a lip seal on, you want to make sure that the lip seal is pressed in. Use a press. Don't hit it with a hammer. I know the socket just fits over top of it, but don't use a socket. What happens when you bang on a seal is you distort the middle of it here, and that changes the amount of pressure that this garter spring puts on the rod, and it will cause a leak. Maybe not today, but maybe will tomorrow. So use a press. Do it right. This is the fit and finish part of the trade. Things don't leak when you do them right. There's nothing worse than putting together a large system and then turning it on and everything works and you see a drip, 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 drip because you have a leaky seal. It's quite annoying. So you want to avoid that. Okay, so when you're cleaning up shafts and cylinders, when you're bringing them in and out of service, if you're cleaning them up with emery cloth, you want to make sure that you don't do the spiral sanding like you have in the top right-hand corner there. What that does is it ends up putting spiral marks onto the shaft, which can end up leaking fluid across. So you don't want to use axial marks either. You don't want to run it over. What you want to do is you want to come backwards and in one direction only and make the marks circumferal so they go around. So emery at right angles to the shaft. That way you make sure that you don't put any swirlies or any channels for fluid to leak through or to rip your seals to pieces, right? So a thimble seal, because of the shape of the lip seal, it fits tightly over the shaft and it may want to roll over. So it's very careful when you're putting these together that they're well lubricated. And again, you can use cellophane to make sure that it slides on the shaft and make sure that it doesn't roll over. And hydraulic oil, any seal that's put on should be lubricated before it's installed. It just should be. So mechanical seals are another way of sealing around a shaft when you have pressures of in excess of 150 psi or 10 bar. Sorry, 100 bar. One seal static with shaft, the other static in the housing. Movement exists between the two seals halves, and you'll have a little bit of a fluid film in between, and that's actually forming a what am I looking for? A fluid seal due to the pressure differences on both sides. So it's critical that that fluid film exists because that's actually what's kind of giving a suction cup seal to it. Rod seals. Rod seals provide support for the rod. 3 types of seals: static O-ring. On the outside of the bushing, you'll have your PTFE supports. So, and then you'll have your wiper seal, which will prevent contaminants from getting into the cylinder. Cylinders are often used on excavators and machines that get quite dirty. And those wonderful shiny stainless steel rods that you see on those cylinders stay that way because those wipers, very much like the windshield wipers on your car, are making sure that none of that dirt gets back into the system. But some of that oil is allowed to coat the seal on the way back to prevent corrosion. So critical that those seals are maintained. So we have a different types of rod pressure seals. You've got your typical O-ring, your V-ring packing in here. This is the old school way, and you go around and around and around in a spiral. You've got your U-ring seals, your X-ring seals. your T-ring, and your compression packing. And these are all standard. O-rings now and U-rings with springs and garter springs are pretty much what you're going to see in most of your seals nowadays. They're long-lasting, robust, inexpensive, great. So dynamic O-rings are used for all of your lateral surfaces. For instance, here in these two diagrams, it's a dynamic O-ring is used on the spring compressor there on your pressure transducer, and on the bottom you're seeing it on the thumb screw on the Neal valve. And again, they have a little bit of a looser fit than a static O-ring, and they have a smoother finish, and they'll often have backup rings of PTFE, which will help protect them from being extruded out. So piston seals, these are again for cylinders that are moving in and out. They're metallic, they're hard wearing, they're compatible with high temperatures, they can withstand high pressure. They allow some leakage to lubricate the cylinder when it extends and retracts. They can cause some creep under load because they do leak. And anytime you get a leak, you know, that can be an issue in terms of a creeping load, if it's a suspended load that's coming down, etc. And you can use non-metallic seals as well if you cannot have any creep. But again, those non-metallic or synthetic seals are not going to be as impervious to heat or some of the caustic agents you might find in some industries. Okay, here's rod seals again, and these are two pretty common types. The top type is an older design, and you can even find these still made out of actual leather. And the leather is kept lubricated by the oil. I've seen some older, rather cool pistons that still had leather seals on them. Anyway, of course, nowadays they're being replaced by synthetic fibers, but the cup seal is still used and is quite durable, and it can make a decent seal under load. Right? The T-ring seals, where you'll have a T-ring with a couple of O-rings on either side, is pretty much a common modern design nowadays. They're hard wearing, easily replaceable. All of these parts, of course, are maintainable and can be changed out. So that's a quick trip around the different types of seals that you'll find in industry. And remember that the seals and the fluid have to be compatible. Any kind of incompatibility between the seal and the fluid can damage your seals and cause all kinds of grief and leaks in your system. So the two are quite related. Anyway, we shall talk to you next time, and have a good day.